Patel, Assistant Professor from LJIT. So students, in the last lecture, we will discuss about our example number 1 of foot over bridge, in which we are discussing about through type of foot over bridge. And in through type of foot over bridge, we will discuss about the end type of lattice girder arrangement. Okay. So in N type of lattice girders arrangement, there are main four members. First one is your top chord, second one is your bottom chord, third one is your vertical member, and at last it is your diagonal member. Okay. After calculating the forces on all these members, we will discuss about the design of all the members, and it is discussed that for top chord and vertical member we will design the top chord member and vertical member as a compression member, because the compression force is maximum in this member. After that we will discuss about the bottom chord member and diagonal member. So for through type of truss, our bottom chord member and diagonal member is in compression, so we will design these two components as a tension member. Okay. Now our step number 15, which is our last step, is the design of joint. So design of joint basically means we have to design at which junction how many bolts are there. Okay. So we have to find out bolt values, and you all know that for 20 diameters and for 4.6 grade of bolt, our 20 diameter is in two shears, double shear, because we have to use double angle. So the value of double shear for 20 diameter, it is 90.52 kilonewton. It means if we are fixing one bolt, it takes 90.52 kilonewton loads. So for all the four members, it is top chord, bottom chord, diagonal and vertical. We have to find out number of bolts. So the equation of number of bolts is the force divided by bolt value. Okay, so this is your last step. Now we are moving further to our second step. So our second example is a design of steel foot over bridge for the following data. So the difference between example number 1 and example number 2 is in the type of truss arrangement. Okay. There are 90% of similarities in example number 1 and example number 2. There are some load distributions are difference in this example. So let us revise some similar portion fastly. So the type of truss is Warren type. In the first example, we will discuss about N type of truss. Span of bridge is 18 meter. Width of walkway is 4 meter. Panel length is 3 meter. It means in this example, it is already discussed that our panel length is 6 meters. So there are 6 panels of 3 meter. So our total span of bridge is 18 meter is fixed. Now live load is 5 kilonewton per meter square. Flooring is equal to RCC slab with 120 thick. Floor finish is 1 kilonewton per meter square. And at last assume the suitable data if necessary. Now our first step is the geometry of lattice girder, or it is also called as configuration of trusses. Now as per data given, our type of foot over bridge like this. This is your side view and this is your plan view. Whenever you are show the side view, our trusses will be like this. Okay, so you can see that this is our Warren type of truss arrangement. This Warren type of truss arrangement, in which this is your top chord, this is your bottom chord, and these all are your diagonal members, because there is no vertical members in this type of truss arrangement. Okay. Now the angle between the horizontal, which is bottom chord, and diagonal member is 60 degree. Okay. So if there is no any clarification regarding the angle between the trusses, then you have to consider the 60 degree. Okay. So you all know that the total angle in triangle is 180 degree. So if your one angle is 60 degree, then another two angle is assumed as a same angle. So this triangle is your equal angle triangle. Okay, it means all the angles in this truss are 60 degrees. So this is your truss arrangement from side view. Now, whenever we are show our truss from the plan view, it means from the top of the foot over bridge, our structure system will be like this. Okay, this is your width of walkway. It is already discussed in the last examples. This is your panel length. Distance between the two cross beam is considered as your panel length. So it is given as 3 meter. And this is your width of walkway, which is also discussed in our question that your width of walkway is 4 meter and your total span of bridge is 18 meter. Now your step number 1 is the geometry of lattice girder in which span of bridge is 18 meter, panel length is 3 meter. So if this length is 3 meter, then this length is also 3 meter because this is equal angle triangle. Okay, then first of all we have to find out the height of truss. So if we have to find out this value h, then this h is your unknown. If this length is 3 meter, then the center of this length is 1.5 meter. Okay, so we will use sine theta equation. Okay, and we will get our answer, or you can also use tan theta equation also. So tan 60 degree is equal to h divided by 1.5. So our value of h is 2.59 meter. So 2.59 is nearly equal to 2.60 meter. Now there are two methods of to find out the length of diagonal. First is, if the angle between all the trusses is 60 degree, it means it is your equal angle triangle. And when the angle of all the trusses are remain same, then it is obviously the distance between all the truss and the truss length is also remain same. So for equal angle triangle, your length of diagonal is also 3 meter. And with the help of Pythagoras equation, you will get your answer of length of diagonal. So it is 3 meter. Okay, so this is the end of your step number 1. Your step number 2 is design of cross beam. So you can see that in this figure, this is your cross beam. And it is already discussed in the last example that your end cross beam takes half of the load and your intermediate cross beam takes the full load, because the half of the load is coming from left side and half of the load is coming from right side. Okay, so in this example the panel length is 3 meter. It means 1.5 meters load is transferred to the left side to cross beam and 1.5 meters load is transferred to the right side of cross beam. Okay, so your intermediate cross beam takes 3 meters of load. Now it is already discussed that there are main three components load which transfer to the cross beam. So it is sulfate of cross beam, sulfate of RCC slab, floor finish and live load. So sulfate of RCC slab, it is 25 into 0.12, because in the question it is already discussed that the flooring thickness is 120 thick. So it is 3 kilonewton per meter square. Floor finish is 1 kilonewton per meter square and live load is 5 kilonewton per meter square. So your total load which is transferred from the upper system to the cross beam, it is 9 kilonewton per meter square. Now as discussed earlier that your intermediate cross beam takes full load. It means 1.5 meters load from left side and 1.5 meters load from right side. So total 3 meters load are transferred to the cross beam. So 9 into 3, so it is 27 kilonewton per meter. Now The self weight of cross beam is also to be assumed whenever you have to design any structural component, then the self weight of that component is also to be considered. Okay, so in this example, we have to assume that the self weight of cross beam is 0.5 kilonewton per meter. So now our total load is 27.5 kilonewton per meter. Now this total load is your unfactored load, and you all know that whenever you have to design any structural member, then you have to design for factored load only. So now we have to find out total factor load. So the equation of total factor load is unfactored load into factor of safety. So the value of factor of safety is 1.5, and total unfactored load it is 27.5, and you will get your answer 41.25 kilonewton per meter. Now this 41.25 kilonewton per meter load is transfer on the cross beam in the width of walkway, which is 4 meter. Okay. After finding out the value of the load, we have to find out main two steps, which is the maximum factor moment. So for simply supported beam, you all know that when the simple support beam and the beam subjected to UDL throughout the span, then the equation of moment is WL square by 8, in which your value of W is 41.25, your value of L is 4 meter divided by 8. So you will get your answer 82.50 kilonewton into meter. After finding out the maximum moment, next we have to find out maximum shear force. It means our reaction. So whenever the simple support, because it is simply supported beam, the reaction at both the ends is WL by 2, WL by 2. Okay. So the value of Vp is WL by 2, in which the value of W is 41.25. L is equal to 4 meter divided by 2. So you will get your answer 82.50 kilonewton. Okay. Now next is we have to find out required plastic section modulus, and this equation is derived from this equation, because it is already discussed that whenever we have to design, then we have to trial and error. So for trial and error method, you all know that whenever you have to design any structural component, there are two main points keep in your mind. First is your component is safe, and second one is your component is economical. So for economical point of view, there are four class of structural members are there for steel structure. Class 1 is for plastic, class 2 is for compact, class 3 is for semi-compact, and class 4 is for slender. Now there is class 1, 2 and 3 is given in your IS 800 2007 on page number 18. Okay, so your last weakest member is class 3. So if we are assuming that our section is semi-compact, then you can see that for semi-compact section, your value of beta B is ZE by ZP. If we are putting the value of beta B is equal to ZE by ZP in this equation, so our equation of ZE is like this, okay, in which the value of MP is our 82.5. So it is 82.5 into 10 raised to 6 into 1.1 divided by 250. So we will get our answer 363,000 mm cube. It means if we have to design any structural members which takes 82.50 kilonewton into meter moment, so we have to design a member like this, in which the member's maximum ZP is greater than 363 cm cube, and the value of ZP is given on IS 800 2007 on page number 139 134 0. Okay, So you can see that on page number 139, there are last second column, plastic modulus, and the value of plastic modulus is given in cm cube equation. Okay, cm cube unit. So from this column, we have to select our member having the value greater than 363 cm cube. So for this example, we have to choose this section which is 443.09, and this section is your ISLB 275, which having the sulfate of 33 kg per meter. So let us try our ISLB section 275, which have the load of 33 kg per meter. It means 1 kg is equal to 10 Newton, and exactly it is 9.81 Newton. So 33 kg per meter is equal to 330 Newton per meter. Okay, so let us try our first section, and after selecting the section, first of all we have to classify the property of the section. So for this section, these all the values are finding out from steel table. So your first value is capital D. Capital D is also called as depth of section. It is equal to 275 mm. ZP is 443.09 cm cube. BF means width of flange. It is equal to 140 mm. TF is equal to 8.8 mm. TW is equal to 6.4 mm. IZZ it is equal to 5375 into 10 raised to 4 mm raised to 4. Capital R means radius of root. Okay, this curvature at this junction is called as radius of root. So it is 14 mm, and ZP is 443.09 cm cube, which is greater than our required cm cube. Okay, now let us check our selected section in which state, in which class of section. Okay, so for section classification, you all the students are moved to page number 18. So on page number 18, you can see that your first row, outstanding element of compression flange, in which there is two parts. First one is rolled section and second one is welded section. So you all the students are moved to rolled section, in which the equation is B by TF. Now TF means thickness of flange, but what is B? So the value of B is BF divided by 2, and it is clearly mentioned on page number 19, in which there is figure number 1. In which figure number 1, it is clearly mentioned that your value of B is BF by 2. So after putting all this value, you will get your answer 7.95 epsilon, and this 7.95 epsilon is less than 9.4 epsilon, which is for class number 1 for plastic. After calculating for flange, next member is for web. So for web, and you all know that your I section is your symmetric section in both the ways. So for I section, your neutral axis at the mid depth. So you all the students are moved on the fourth row, in which it is clearly mentioned that web of an I, edge and box section, in which there is one row, thin row, in which it is clearly mentioned that neutral axis at mid depth. So for this section, the equation is d by tw. So the equation is, what is small d? Small d is the depth of web portion. So the equation of depth of web portion is capital D minus 2tf minus 2r. So after putting all this value, we will get our answer 35.84 epsilon, and this value is also less than 84 epsilon. So If your selected section of wave is in plastic section, for wave it is also in plastic state, it means your selected section is in plastic state. Okay students, so this is the end of your step number 2. Now step number 3 and step number 4, which is the check for moment capacity and check for shear capacity, is discussed in our next lecture. So students, this is the end of today's session. Thank you.